look at Theorem 4.5, and we'll talk about this a little bit more as the chapter goes on. But for this, we have the antiderivative of the derivative of f of x. Remember, these two things, the antiderivative and the derivative, are inverses. They're opposites of each other. So they kind of undo each other. Just like if we had the square root of something and then squared it, those things cancel each other out. Or if we added 5 and then subtracted 5, those are inverse operations. They cancel each other out. So knowing that, if we do the antiderivative of the derivative, what do you think we're going to end up with here? The original, right? Just the f of x. But there's a little twist to this one. It's not just f of x. It's going to be f of x plus c. Right? Because the antiderivative is the last thing we would do. And we'll look at some examples of this later. But if we take the derivative of the function and then take the antiderivative of the function, we basically end up back where we started. But we have to take into account that the antiderivative, there's lots of possible answers. So we have to have that plus c. So it's kind of like when we do like inverse sine, inverse cosine, those types of things, where it's not as simple as just kind of canceling out. You have to kind of remember that. For this one, again, we have those opposites, the derivative and the antiderivative. But this time, it does end up being just f of x. Because we do the antiderivative first, so that we'd have a plus c involved. But then when we take the derivative of a constant is 0, so it cancels out. Again, we'll kind of come back to these two theorems as the chapter goes on. But let's take a look down here. This table is full of things that you're going to need to remember and just kind of memorize. First one, derivative of x. Kind of like what we were doing on the last page. What's the derivative of x? It's not your question. Okay, there you go. 1. Thank you. Take those brains out of hibernation. So our derivative is 1. If we take the antiderivative of 1 dx, what do we get? X plus c. Right, so whenever we take the antiderivative of just 1, or even just a constant, we're going to take that constant times x and then plus c. Now, this next one looks more complicated than it actually is. If we take the derivative of this, we're going to take that r plus 1 and bring it out in front, which cancels out with the r plus 1 on the bottom. And then we'd have to subtract 1 from the exponent, right? It's just the power rule. This ends up giving us x to the r. Right? So antiderivative of x to the r dx is going to give us this ugly mess. And again, it's not as bad as it looks. We get x to the r plus 1 divided by r plus 1 plus c. So basically what's happening here, this is kind of like the opposite of power rule when we do the antiderivative. There's two things happening. We're adding 1 to the exponent, and then we're dividing by the new exponent. Right, we're adding 1 to the exponent and then dividing by the new exponent. And that should kind of make sense if you think about it. Antiderivative is the opposite of the derivative. So if we look at an old derivative equation, or simple one, we take the derivative of x to the 5th. Well, how did we do that? We multiplied by this exponent, right? We put the 5 out in front, and then we subtracted 1 from the exponent. Well, the antiderivative is doing the opposite of that. Instead of multiplying, we're dividing. Instead of subtracting 1, we're adding 1. So antiderivative is just doing the opposite of what we did with the power rule. And we'll look at some examples of that in a little bit. But the rest of these are all the trig derivatives. So derivative of sine is cosine, which means the antiderivative of cosine is going to be equal to sine of x plus c. All right, the derivative of negative cosine would be positive sine of x. So the antiderivative of sine of x is equal to opposite of cosine of x plus c. right? So it's just going backwards. So you don't necessarily have to memorize these antiderivatives. If you know the regular derivatives, you can kind of work backwards, but the memorizing kind of makes it a little bit easier. Derivative tangent is secant squared. So that means the antiderivative of secant squared of x is going to be tangent of x plus c. Derivative of negative cotangent is cosecant squared of x. Antiderivative of cosecant squared is going to be negative cotangent of x plus c. Derivative of secant is secant tangent. So antiderivative of secant of x tangent of x dx would be secant of x plus c. And then our last one here, derivative of negative cosecant would be cosecant of x, cotangent of x. So antiderivative of cosecant of x, cotangent of x dx would be negative cosecant of x plus c. All right, just a couple more things here with like kind of rules with antiderivatives. If we take the antiderivative of a constant times a function, just like derivatives, just like limits, when we have that constant there, we can kind of pull it out in front, kind of keep it separate. So we can take the constant out in front of the integral times the antiderivative of f of x dx. And with addition and subtraction inside the integral, we can split that up into two separate parts. So for part b, we can rewrite this as antiderivative of f of x dx plus the antiderivative of g of x dx. So it helps sometimes to take a bigger function and split it up into smaller ones so they're a little bit more manageable to take the antiderivative. Same with subtraction here. And we're not going to write it out this way every time. We're not going to split up the integral in writing, but in our heads we're going to kind of do that. We're going to take the antiderivative of each part individually when we have addition and subtraction.